In the last several videos, what we did was looked at electrophilic aromatic substitution reactions starting with benzene. Now, and for the next several videos, we go into the next phase of our electrophilic aromatic substitution lives by looking at the concept of directing groups. Directing groups refer to scenarios where we start with an aromatic ring that already has one or more substituent on it, such as the case of toluene here in our example. We're not starting with benzene, we're starting with a benzene derivative. And we refer to the group that is already attached to the aromatic ring as a so-called directing group. It is going to direct the course of the reaction in terms of where the next electrophilic group will bond to the aromatic ring. And so in this example that I'm showing here, we start with toluene as one random compound, one random example of a substituted benzene ring. We're doing a Friedel-Crafts acylation reaction. We recognize this Friedel-Crafts acylation from our earlier videos because we have a mixture of aluminum chloride catalyst with our acyl halide reactant. And we've recognized from that reaction type that generally what was happening there when it reacted with benzene was that one of the hydrogen atoms from benzene was replaced with the acyl group, like we're seeing here, here, and here. The difference between the earlier scenario where we were reacting with benzene and what we're doing now is in the case of benzene, it didn't matter at all which atom of the aromatic ring you bonded the acyl group to because the product was going to be the same. In the case of a substituted aromatic ring as our starting material, like toluene here, we've got another challenge to deal with because of the fact that there are three possible constitutional isomer products. Anytime you're starting with a molecule that has one group already on it, and you're bringing in a second group, the three possible constitutional isomer products would correspond to the ortho substitution pattern, where we have the branches at positions 1 and 2, the meta, where we have the two branches coming off at positions 1 and 3 relative to one another, and then the para, where the two groups are directly across from one another at the 1 and 4 position. And so in this electrophilic aromatic substitution reaction, as we start thinking about directing groups, we have to ask ourselves, how can we use the structure of the group that's already on the molecule to determine what the preferred constitutional isomer products or product will be from this electrophilic aromatic substitution reaction. And in this video, we are going to outline what groups, what specific so-called directing groups will direct the reaction toward each of these types of products. In the upcoming video, we're going to look at reaction mechanisms that will explain the observations that we can make empirically about what types of constitutional products will be provided based on the starting material that we begin with. So we're looking here, kind of in the big picture thing, we are looking at what is, or we're trying to answer, what is the regioselectivity of these reactions. We're asking what constitutional isomer do we prefer to make, and that is the concept of regioselectivity. So we're looking at what is the regioselectivity of this particular reaction. And as we do this, as we talk about directing groups, the concepts that we are going to be focusing on here, and we'll get into mostly in the upcoming videos, that when we are talking about directing groups are what we refer to as groups that are going to guide the reaction based on electronic effects. So directing groups are going to guide the reaction to specific constitutional isomers, ortho, meta, or para, based on electronic effects. And when we think about the outcome of reactions in general, there are what we refer to as electronic effects, which have to do with the electron densities and the stabilities of carbocations and things of that sort, things that are driven by electrons and charges. And then there are also what we refer to as steric effects, which refer to effects that are dealing with crowding within the molecule. And so when we talk about directing groups are specifically evaluating the impacts of so-called electronic effects on the outcomes of reactions. And we will see how these so-called electronic effects come into play when we look at the mechanism for these reactions in upcoming videos. But for now, what we're going to do is just define what would we observe as some outcomes of the presence of specific directing groups attached to the aromatic ring from the onset. So rather than starting with benzene as our starting material, we're starting with molecules that already have some sort of group attached, and we refer to that group as a directing group because by electronic effects, it's going to drive the outcome of the reaction to steer it towards specific constitutional isomer or isomers. So now to dive into the identities of particular groups that you may run into as directing groups, we're going to look at this chart, which is available to you in the handout for chapter 17. If you're on Canvas and go under the module for this chapter, you will find this particular handout. So what we're going to do is spend the next few minutes dissecting this handout in order to prepare us for predicting the major organic products of reactions where we start with a benzene derivative, meaning that if we start with toluene or we start with phenol or we start with nitrobenzene, how do we predict what constitutional isomer will result from an electrophilic aromatic substitution reaction of that? And one of the key tools for doing that is going to be understanding this particular chart. So let's start from the top here. So at the top, we see groups that are labeled as so-called orthoparadirecting. And remember that when we say directing, what that meant was that by electronic effects, which we'll get into in the next video, the group that is already attached to the aromatic ring at the onset of the reaction is going to direct the outcome of what constitutional isomers result from the reaction. And so in the case of these orthoparadirectors, what this is telling us is that any of these groups that I'm circling with my laser pointer, anything through here, if that group is bonded to the aromatic ring from the beginning of the reaction, then the products of the reaction are going to correspond to putting the next group at the ortho and para positions relative to where the group was at the start. And so what you will notice here is that of these so-called orthoparadirectors, what's going to be true for all of them is that if we start with an aromatic ring that has what I will refer to as OP on it, where OP is our so-called orthoparadirector. That means any of these groups that I'm circling up top here, so anything that's in green or purple boxes, would be an orthoparadirector because that corresponds to this part of the chart here. We react that in an electrophilic aromatic substitution reaction. Pick your favorite electrophilic aromatic substitution reaction of the ones that we talked about in the earlier video. So I'm going to do bromine and iron tribromide catalyst. We recognize that as one of our electrophilic aromatic substitution reagents that replaces a hydrogen from the ring with the bromine. And so if we have an orthoparadirector already attached to the ring from the start, that orthoparadirector is going to direct the outcome of the reaction so that the bromine bonds at the ortho position here, and the other constitutional isomer product is going to correspond to the bromine bonding at the para position. And both of these products, the ortho and para products, would form in equal quantities based on these so-called electronic effects of the directing group. So the directing group, much like the director of an orchestra, tells the rest of the orchestra what to do. The directing group is going to direct the bromines about where to go. And the bromines are going to go to the ortho and para position if you start with a so-called orthoparadirector on the aromatic ring. And so that would correspond to such compounds as aniline, because aniline has an NH2 group directly attached to the aromatic ring. Acetanilide has a nitrogen directly attached to the aromatic ring and then a carbonyl and a methyl, so that would fit this template that I'm circling up at the top. Phenol, which has a hydroxy group directly attached to the aromatic ring, would qualify. An alkyl group would result in orthoparadirection, and any halogen that's directly bonded to the ring would result in the reaction being guided toward the ortho and para products. On the flip side, if rather than an orthoparadirector being directly attached to the aromatic ring at the beginning of the reaction, if instead there is a so-called metadirector attached to the ring at the beginning of the reaction, what's going to happen is that the product of the reaction will be meta. That will be the major organic product. And so metadirectors include all of the groups that I'm highlighting right here. Everything boxed in red is referred to as a metadirector, meaning that if we start a reaction with any of those metadirectors attached to the aromatic ring, so I'm going to put M here indicating that this is any of those metadirectors, and it has to be the exact arrangement of atoms here, meaning that the bond that we are seeing here that I'm highlighting in the red box, that bond is what connects to the aromatic ring. So what we see on the left side of each of these dashes would have to be directly connected to the aromatic ring. So in other words, if we have a carbonyl directly bonded to the aromatic ring, it's going to direct the reaction toward the meta position. If on the other hand, the carbonyl group is somewhere else in the chain further out, like we have a nitrogen atom up top here, and then a carbonyl group, the reaction is going to be directed toward the orthopara position. And so the order of these atoms in these groups is essential. And keep in mind that what we're looking at is that where the bond goes indicates where the aromatic ring would have to be for these. So under this category of metadirectors, if we have an aromatic ring directly bonded to a carbonyl, that's going to direct the product toward the meta position. And so what we can show that as schematically here is just a generic example at the bottom, is that if we have a metadirector, any of these groups directly bonded to the aromatic ring, and we subject it to an EAS reaction, any EAS reaction, so I'm going to use bromine reacting here as my example for this case, then the product of the reaction is going to correspond to having that metadirector still present there on the ring, and then the other group, the bromine in this case, is going to bond at the meta position. So I'm going to put the bromine here at the meta position relative to that metadirector. And so you will want to be very, very familiar with this chart, because one of the things that you are going to be tasked with doing pretty frequently is determining the product of a reaction that already has one branch coming off of the aromatic ring, and then you're bringing in a second branch via an EAS reaction. You're asked what constitutional isomer or isomers are going to result from that. And so in order to accomplish that, you will have to be familiar with this chart. There are some general trends that we can notice from this chart that will be helpful in avoiding rote memorization of this information, because you may need this information if you're going to be doing things like the MCAT or the PCAT or the GRE standardized test in chemistry. You won't have this sheet handy to refer to as you're doing those types of things. And so one thing to keep in mind is that these groups that are toward the top here, that are orthoparadirectors, all have lone pairs directly off of the aromatic ring. That is one of the features that will enable a group to act as an orthoparadirector, is that it has lone pair electrons on the atom that is directly attached to the aromatic ring. So keep in mind the aromatic ring is here, 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 etc. at the end of that line. In all of these cases, all of them have, highlighting this, a lone pair, lone pair, lone pair, lone pair, lone pair, lone pair, so on and so forth. At least one set of lone pair electrons directly attached to the aromatic ring. That is going to always cause a group to be an orthoparadirector. The same is true down here with our halogens. They all have at least one lone pair of electrons directly attached to the aromatic ring. And so that is going to cause a group to automatically be an orthoparadirector. So anytime you see lone pairs directly off of the aromatic ring, that is always going to be a so-called OP director, an orthoparadirector. So when you look at a structure and you're like, there's lone pairs directly attached to the aromatic ring, automatically say to yourself, that's an orthoparadirector. Even if it's something that's not directly on this chart, lone pairs directly attached to the aromatic ring are going to create a situation where the orthopara products are preferred, where we have an orthoparadirector like this top scenario here as we look at the example toward the bottom of the screen. On the other side of the spectrum, metadirectors will be true anytime you have a pi group, a carbonyl group specifically, directly attached to the aromatic ring. So notice how all of these groups I'm highlighting in blue toward the bottom here all have that carbonyl group directly attached to the aromatic ring. And that is going to cause those groups to be metadirecting. So it doesn't matter what else is bonded out here further away from the aromatic ring. If you have a carbonyl group directly attached to the aromatic ring, then what will always be the case is that the group will be a metadirector. Analogously, if you have a sulfonyl group, that sulfur-oxygen pi bond is going to cause the group to be metadirecting. And likewise, the nitrile group, carbon-nitrogen double bonded, or triple bonded rather, is going to behave analogously as well, because this is pretty similar in terms of structure and bonding to the carbonyl group, because you have a carbon that has some pi bonds to an electronegative nitrogen, similar to here where you have a carbon directly bonded to an oxygen with a pi bond going on. And then down here further, these are all situations for these metadirectors where we have nitrogen atoms, that is electronegative atoms, with no lone pairs. So I'm going to label this as electronegative or eneg, electronegative atoms with no lone pairs directly attached to the ring. So this is a very different situation down here at the bottom than what we were looking at up top, because at the very top of the chart we had nitrogens that had lone pair electrons. Down here at the bottom we have nitrogens where if you drew out the Lewis structure, we see there's no lone pairs directly attached to the aromatic ring atoms. And so, therefore, those end up being metadirectors. Likewise, we have CF3 and CCl3. That's carbon atoms that have very strongly electron withdrawing groups attached to them. So carbons with strongly electron withdrawing groups are going to send the reaction toward the meta position. Highlighting one additional point off the chart, which we didn't discuss previously, R seems pretty generic. R is always here in this chart referring to an alkyl group. So if you have a methyl group, ethyl group, tert-butyl group, whatever your favorite alkyl group is, that is going to be an orthoparadirector. So you'll want to be familiar with this chart in terms of using it to predict the outcomes of reactions. In the upcoming video, we will look at, from a mechanistic perspective, why it is the case that some of these groups will direct the reaction toward the orthopara product, others will direct toward the meta product. We will also look in depth at why we've used this terminology here, starting at the top of strongly activating to going to the bottom of these groups being strongly deactivating. We'll look at the molecular basis for why the groups at the top are strongly activating, why the ones as we come down the sheet are strongly deactivating, and what we mean when we say activating versus deactivating without going into the mechanism of it. Activating means that this will react faster than benzene. So in other words, having that group, such as an amine group bonded to the aromatic ring, makes it react faster than if you just had the naked benzene ring reacting. On the other hand, when we come down to the bottom of the chart, when we say a group that's attached to the ring is strongly deactivating, that means it's going to cause the reaction to occur much slower rather than faster. It's going to occur much slower than the same reaction with benzene. So we're looking here at how readily the reactions take place based on the directing groups that are attached. So in total, the directing groups are going to determine both the outcome of the reaction in terms of the regioselectivity. Those directing groups are also going to determine how quickly and readily the reaction is able to proceed, where if you have a strong activating group, you can expect the reaction is going to go really fast and easy. If you have a strongly deactivating group attached to the ring from the start, you're going to imagine the reaction will go much slower than if you were reacting with benzene. And so in looking at these reactions, we can go ahead and do an example here of predicting the product or products of a particular electrophilic aromatic substitution reaction based on the information that we have in hand here. So let's take a look at these two example problems where we are tasked with predicting the major organic product of each reaction and include the phrase here based on electronic effects. Electronic effects we could think of as synonymously with based on what directing groups are bonded to the aromatic ring. In some of the later videos, we will get into what we refer to as steric effects, which refer to the crowding of the molecule, which can help guide it toward certain constitutional isomer products. For example, in some cases preferring the para product, which is less sterically crowded than the ortho product. But electronic effects are the first thing that we consider when we determine the outcomes of these reactions. And so, therefore, we're going to be predicting the major organic product based on electronic effects. And so if you see the phrase based on electronic effects, just be thinking that electronic effects are what are described in this chart here of ortho, para versus metadirectors. And so you want to use that information to determine the organic products of the reaction, where we are going to start with isopropyl benzene, react with tert-butyl chloride and aluminum trichloride. I encourage you to hit pause, try to sketch out what you would expect the product of this reaction to be to see if you are on the right track here. So I'm going to go ahead and draw out the product of this reaction. So I recognize tert-butyl chloride and aluminum chloride as being the mixture of reactants that will create a Friedel-Crafts alkylation reaction, with the aluminum chloride acting as the catalyst to enable the transfer of the alkyl group onto the aromatic ring. So we're going to be transferring the tert-butyl group onto this aromatic ring. We started with isopropyl benzene, so we're going to finish with isopropyl benzene here, and we are also going to attach that tert-butyl group on somewhere. So in order to determine where the tert-butyl group is going to go, we need to evaluate whether the group that is on the ring to start with is an orthoparadirector or a metadirector. It doesn't matter what the identity is of what's entering the molecule. So the tert-butyl chloride, aluminum chloride doesn't make a difference at all in determining whether we are going to create the orthopara products or the meta product. What matters is this directing group, what's already attached to the aromatic ring from the start. So what's already attached to the aromatic ring from the start is an isopropyl group. That is going to qualify as, remember that on our chart here, R was referring to an alkyl group. And so alkyl groups are in the part of the chart that corresponds to orthoparadirectors. And so I'm just going to remind myself by labeling this starting structure that this is an orthoparadirector. And therefore, what that means is that what we're bringing in, our tert-butyl group, needs to go at the ortho position. So I'm going to place it here. And then the other constitutional isomer product of this regioselective reaction is going to be with the tert-butyl group at the para position, since the starting material had an orthoparadirector attached to it. So we're going to make the ortho and the para products here based on these electronic effects of the directing groups. So those are going to be our two organic products that we would need to draw out here if you were asked to show the major organic product or product of that reaction. You would be right on track there with this answer. Next one in line, we are going to go ahead and start with our molecule that has a carbonyl group directly attached to it. Anytime we have a carbonyl directly attached, it is going to be a metadirector. So we're fitting the paradigm down here toward the bottom of the chart here. Specifically, we'd be looking at this scenario that I'm circling here, but it doesn't matter if you have a carbonyl group directly attached to the aromatic ring, it's definitely going to be a metadirector. And so I'm going to put that in as meta director to remind myself that I need to make a product that is meta relative to where that starting R group was, our R group here being the ketone group. So there's our ketone group, and then meta relative to that, I will plug in the group that will be coming in here, and that's based on what we're reacting with. We're reacting with a mixture of nitric acid and sulfuric acid, which we said back in one of our earlier videos created a nitration reaction where you end up bringing in a nitro group, an NO2 group, into the reaction. And this will be the only constitutional isomer product of this reaction, because of the fact that we're dealing with a metadirector here, that is going to be the major organic product, not the ortho or the para. So what about this scenario where we start with an aromatic ring that is already di-substituted? So we start with an aromatic ring, in other words, that already has multiple directing groups attached to it, and we want to bring in an electrophile for electrophilic aromatic substitution. How do we decide the regioselectivity of that reaction? The rule is, if there are already two directing groups on the ring and we're deciding what to do in the electrophilic aromatic substitution reaction, is that in electrophilic aromatic substitution, the stronger activating group drives the regioselectivity. And so, in other words, we could think of this chart here as we go up the chart. These groups are most important in determining the regioselectivity. And as we go down the chart, these groups are least important. And so if you have two groups attached to the ring, you will need to assess which one of those is higher up in the chart, which one is more strongly activating based on our schematic here. The one that is more strongly activating is going to be the one that dictates the regioselectivity of the reaction. So activating groups outweigh deactivating groups in determining the regioselectivity of these reactions. And so as an example of this, if we have an aromatic ring, which has, let's say, we will put a methyl group on there, and we will put a, let's do over here, let's do a nitro group. And we'll go ahead and react that with, let's do chlorine Cl2 with iron. We could list it as just iron. We could also list it as iron trichloride. And so in order to determine the outcome of this reaction, we needed to assess these two directing groups. And this directing group, the alkyl group, falls right here as that R group there. We describe that as being weakly activating by looking at where it is at on the chart here. It falls in the weakly activating. The nitro group, down here at the bottom, falls into the strongly deactivating part of the chart. And when you are determining which of these is going to drive the regioselectivity of the reaction, it's always going to be the one that is more activating or less deactivating. So as we go up the chart here, as I said, there is increasing importance in determining the regioselectivity. And so since the alkyl group is higher in the chart, more activating in other words than the nitro group, the methyl group is what is going to determine the outcome of the reaction. So this weakly activating methyl group is going to be the driver of the regioselectivity because it is the group that is higher up in the chart. It is the more strongly activating of the two groups, or the less deactivating, however you want to look at it. And so, therefore, the product of this reaction is going to correspond to the orthopara product because the methyl group is an orthoparadirector. It fits up at this top part of the chart that was where the orthoparadirectors lived. And so, therefore, our product or products of this reaction going to correspond to having our aromatic ring with our methyl group and our nitro group. And then in determining where we put the chlorine atom, since our methyl group is what is driving the outcome of the reaction, we can place our chlorine atom right here. That would be at the ortho position. We could also equivalently have put it over here where I'm highlighting with my laser pointer. That would have created the exact same constitutional isomer. But here's ortho right here. And then additionally, we could envision putting the group at the para position, but the para position is already occupied with a nitro group, and so therefore we can't get rid of the nitro group in order to put a chlorine atom in there. That would be some funny chemistry going on, and so therefore this is actually the only constitutional isomer that we will create as a major product from this reaction, because of the fact that even though we're dealing with a methyl grouping in orthoparadirector, the para position is already occupied, and so the ortho position is the only place for that chlorine atom to go. It's not going to go into that meta position because of the fact that our directing group here that dominates is our methyl group, because the methyl group is further up in the chart. It's more strongly activating. Activating groups speed up the reaction, and hence the reaction leading to the chlorinated product at the ortho position is much, much faster than the route to the meta position would be. And so that activating group, being the activating group speed up the reaction, is going to dominate in determining the outcome. And the outcome here is that we end up with a product at the ortho position of this molecule. In the upcoming videos, what we are going to do is dive into this phenomenon later of directing groups to look at the mechanisms for some of these example reactions to determine at the mechanistic level why it is that we observe these phenomena about directing groups and the preference for ortho-para products and the observed preference for meta products, explaining it from the level of the individual molecules and the electrons.